afternoon. My name is Iryna Gryn, and I would like to present to your attention this work about reconfigurable patterns of smectic A-liquid crystal defects. In the past few years, smectic A-liquid crystals have emerged as a very promising class of materials for creating large area periodic micropatterns that may be used in various applications such as guided assembly of dispersed colloid and nanoparticles. For this reason, I would like to talk today a little bit about smectic A-liquid crystals, what kind of defects and patterns can be formed in such materials, and about the applications of such patterns. But the main part of the talk would be focused on how can we create patterns with predefined parameters, and about two parameters that allow us to control the periodicity and the symmetry of these defect patterns, such as thickness and electric field. So let me start from the defect and patterns in smectic A-liquid crystals. Smectic A-liquid crystals are made from rod-like molecules that tend to align with each other along one common direction that's called director. And this direction can be determined by anisotropic interaction with boundaries or by the applied external fields. Also, these molecules in smectic A-liquid crystals tend to form layers of equal thickness. And typically, smectic A-liquid crystal fields are confined between two different interfaces imposing different anchoring conditions. For example, planar anchoring, when the molecules aligned in plane parallel to the substrate, and such interface as an air, which induce homeotropic anchoring, when the molecules aligned perpendicular to the substrate. And if we have such an anchoring conditions, you see that there is a competition between different type of anchoring. So to satisfy these anchoring conditions while keeping the layer spacing equal, what the smectics have to do is to bend the layers. In such a case, there are a few different scenarios that we can observe. When the planar anchoring is degenerated and there is no particular in-plane alignment and another interface induces homeotropic anchoring, we will observe axially symmetrical toroidal focal conic domains and hexagonal lattices, which polarized optical image you can see here. Such materials can be used for creating superhydrophobic surfaces and microlenses arrays, and it has been shown that such patterns can interact with colloids and induce some particular ordering for dispersed colloids. In case of unidirectional planar anchorings, there are also different scenarios that can be observed. If the thickness of smectic field is larger than some critical thickness, again we will have non-toroidal focal conic domain formations and two-dimensional hexagonal lattices. If the smectic A film thickness is smaller than some particular critical thickness, we will have one-dimensional linear defect array formations. So now you see that thickness appears to be a very important parameter for such a liquid crystal, and it was also shown that for one-dimensional array of liquid crystal, small particles such as quantum dots or golden nanoparticles can be trapped inside the defect forming straight chains, and it was shown for metallic nanoparticles that they have a polarization-dependent plasmon resonance. So what happens when we have a smectic A film thickness in the range close to the critical thickness? We will observe two different types of patterns, and it appears very important to be able to control the thickness of smectic A-liquid crystal field. For this reason, we switch to another geometry where we confine our smectic A-liquid crystal between two rigid electrodes that were treated in a way to impose conflicted anchoring conditions, such as unidirectional planar anchoring on one substrate and homeotropic anchoring on another substrate. In this case, we were able easily to change the thickness of the cell just by varying a spacer. And there are some another advantages that the wettability issue was resolved, so that we were able to use different liquid crystals and different substrates, varying anchoring conditions, and in addition, also we were able to apply an electric field, which I have said we applied perpendicular to the substrates. Here further, we used mostly polarized optical microscopy, and the images that I would show you were taken under the cross polarizers. Controlling the pattern morphology thickness. As for our measurements, have revealed that for the thickness of the smectic liquid crystals smaller than 1.3 micrometers, we had only one-dimensional linear defect arrays. When we further increase the thickness, linear defect arrays coexist with patches of hexagonal focal conic domains. And when the thickness of the liquid crystal was larger than 2.2 micrometers, only full packed focal conic domain lattice were observed. For both linear defect domains and focal conic domains, period as a function of its thickness increased linearly with the different slopes and offsets. And as you can see in the coexistence region, their sizes were compatible. In particular, for the linear defect domains, we obtained a slope 2 and the intercept 0.3 micrometers. This slope 2 can be explained with a model that we propose for a closed, for the smectic liquid crystal in a closed cell, which is quite similar for the one proposed for open cells, where you can see that the smectic layer starts and ends on the surface inducing planar anchoring vertically while passing the flat and horizontal region close to the surface inducing homeotropic anchoring, so that all these conflicting anchoring conditions were satisfied. And as for the slope 2, you can see that while we increase the thickness of the liquid crystal field by one layer, we have to add two smectic layers from the sides of the domain, so that period increased twice as the thickness. Phase retardation measurements that were taken in the most divergent region of the linear domain revealed that that we have the local divergence value 0.13, which is close to the maximum divergence of ACP at the room temperature, which means that in those regions molecules have to be almost planar along the liquid crystal thickness. Another observations taken under the cross polarizer while rotating the sample revealed that there are regions that remains dark while we rotate the sample, so that it means that those regions must be almost homeotropic along all the sample thickness. Also, this model shows that close to the homeotropic substrate, smectic layers have to be bent almost 90 degrees, which means that probably locally anchoring conditions were vanished, and there may be some topological defect presence. We expect disclination close to the defect walls and inside the defect pores. Another controlling parameter that we were studied is an electric field. For studying the electric field effect on the smectic liquid crystal patterns, we created cells, quite 6 cells. Without an electric field, we had only focal conic domain lattices in such cells. And what happened when we apply an electric field in the nematic smectic A transition is that we observe a one-dimensional array of linear defects. We tried a different thickness of the cell, a different value of applied electric field, and it showed that for the same thickness of the cell, while increasing the voltage, we observed a smaller period of the linear defects. The dependence period as a function of the thickness, you can see on this graph. It looks very complicated, as for each electric field value we have a different slope, different intercept, but if we consider the period of linear defects as a function not of the thickness but of the inverse of the electric field, as you can see, all these complex curves would be reduced just to a single master curve, where the period of the linear defects depends again linearly on the inverse of an electric field. In this graph, you also can see that again we have a coexistence region where linear defects coexist with focal conic domains, which means that when the value of the applied electric field is not enough, we would be not able to switch to the linear defect pattern. And to explain this behavior and to show you that this behavior is quite similar to the zero field behavior, we have to consider the director field distribution in the nematic phase. So when the electric field is absent, the director would be tilted linearly from the normal to the substrate. And when we apply an electric field in the nematic phase, what will happen is that there will be some region close to the surface that induces homeotropic anchors that will become also homeotropic, so that the region where the director is tilted will be significantly reduced and compressed to the surface-induced planar anchoring. In this case, when we further decrease the temperature so that we have a transition from the nematic to smectic A phase, what would happen is that in the region that was homeotropic, there would be flat layers that would be formed. And only in the regions that where the director field was tilted, linear defect array would form, so that the applying of the electric field have an effect that is similar to the one of compression, where we just reduce the thickness of smectic A fields that are viable to the linear defect creation. And this region that, where we create our linear defect domains in this case would be determined by the electric coherence length. And when we compare our results obtained for the zero field and for applied electric field, what we will have is again the linear dependence with the same intercept 0.3 micrometers, which suggests that probably this model is correct. But as you can see, for the zero field we had a slope 2, and now we have a slope almost 5. That suggests that electric coherence length must be larger. And let's say that its effective length, effective thickness of our sample, and it seems that it must be larger than we expected. And about the pattern persistence. As I told you, we use a sample where when the electric field is absent, we have only focal conic domain lattice. And when we apply electric field, we observed one-dimensional linear defect array formation. So there's a question, what would happen when we switch off the electric field? And the answer is that we still have a linear defect array. It looks brighter, probably because some part of the molecules are now not aligned with electric fields, so it looks brighter, but still the period of this defect pattern is almost the same, it's almost stable. So when we switch off the field, we still have the stable pattern. We try to explain this behavior, and what we think what is the mechanism of this persistence? It's that when we apply an electric field in the smectic phase, to change the period or the thickness of the effective thickness of our sample, we have to flatten some of the layers. It requires formation of new dislocations and moving all defects, which requires a lot of energy. And it seems to be too expensive in the energy terms, so that we are not able to change neither periodicity nor thickness while varying electric field in the smectic phase. So as a conclusion, I want to say that smectic A micropatterns are very interesting material system for both addressing fundamental questions and for using in different applications. And the symmetry and periodicity of the patterns can be controlled using thickness and applied electric fields. And it seems that electric fields had an effect very similar to the reducing of the sample thickness. And as a further work, of course, we try to mix liquid crystal with nanoparticles to use this possibility to create a pattern with predefined properties to transfer some special order to nanoparticles. And the first results are found like that, where you can see hexagonalities with trapped nanoparticles. Thank you very much for being
Thank you, Iryna, for your talk. We have time for questions.
So I see a big amount of results, and my first question: what time, how long period of work is described in this presentation, and how many people work together with you to help you with this? Because for me it's enormous.
As I told you, these results were obtained at the University of Calabria together with my supervisor, Bruno Zappone, and now we are working on the article in collaboration with the House.
Okay, and how long you work with about this?
It's 1 year of my PhD.
Okay. So then the second question, it's related to the phase retardation measurements, and as I understood, it's just you have linear defects on the surface of the smectic, and for me it is interesting how it's possible to make some phase retardation for if you have, as far as I see, it's like micro region of this, and how you measure this phase retardation.
We have an optical microscopy, we insert a compensator, and when you're looking on this most bright region of the defect, use a tilt compensator to change it from the most bright to most dark, and it gives you the phase retardation, where you, for the phase retardation, knowing the thickness of the sample, we can calculate the local coefficients in this region.
It's just microscopical technique. I understood. Okay, thank you.
Any other questions?
Just curiosity. In the slide where you show the effect of the persistence, okay, that one. Okay, the pattern remains the same, approximately, but it seems to me that anyway the segments are longer when you remove the field. Is it just by chance, or is
they're looking brighter. I would not say that they are longer. Just it's because of the change of brightness of this defects and things like that.
Well, because compared with the other picture, of course, this difference is brightness, but the abundance of longer segments seems to be higher.
Yeah, but also you see that there is still slight change in period, and when we are talking about the micron, 0.1 micron, it's a slight change, but it's a change, and yeah, the defects are growing a little bit, but I mean that after switching off the field, we still have a one-dimensional linear defect array, and it's stable. So when we switch off, we have this 1.9 micrometers, and it remains 1.9 micrometers.
Any other questions? If not, let's thank the speaker again and all the speakers of the session.